Today we're looking at a 6-mark induction question. You might not have seen it in this form before where it uses the derivative, follows the same principles. Let's get into it. Whatever question you're doing with induction, the first thing you're going to do is the base case. So that means check that the formula works when n is equal to 1. The left-hand side, when n is equal to 1, is going to be the first derivative of x squared e to the x. Like this. To differentiate, we're going to use the product rule. I'm going to write down the first function and differentiate the second. It's not going to change. And then I'm going to write down the second function and differentiate the first, like this. The right-hand side, if I sub in n is equal to 1, it's going to be 2 times 1x, so 2x. And this is going to be 1 times 1 minus 1, which is just 0. So if I expand this bracket, x squared e to the x plus 2x e to the x. Do you notice that those two are the same? That's pretty good. It'd be a pretty rubbish question if they weren't. So left-hand side equals right-hand side. Therefore, it is true for n is equal to 1. And that concludes the base case. That means that the very first value it works for, great. Now we have to make sure it works for all the others. The next step is the inductive hypothesis. So in this step, we basically say, assume it's true for a different letter. Usually we use k. So assume that the whole expression is true for k. We use k rather than n because n is what we're trying to prove, and we're just getting away from that by using this other letter. Essentially, I've written the same thing again, but we're changing all the n's to k's. Now, we want to think about what happens when n, the original n, is k plus 1, so it's 1 higher. Well, let's think about the left-hand side. We'll be looking at the k plus 1th derivative of x squared e to the x. And you've got to see this as you are taking the derivative of the kth derivative of x squared e to the x. You might see now why we wrote this as k, because these two are exactly the same. So this will be equal to the derivative of, big bracket please, all of this. So x squared plus 2kx plus k minus 1 e to the x, like this. We need a bit more space. Now we can differentiate this. So what's this again? It's two things times together. It's another product rule. So what I'm going to do is I'm going to write down the first thing exactly the same. So x squared plus 2kx plus k times by k minus 1. Write down the derivative of the second thing. So again, it's e, it's not going to change. And then I'm going to write down the second thing, I'm not going to change it. And then I'm going to differentiate this big bracket. So that's going to get 2x plus 2k. That's just a number, so that's going to disappear. I'm going to put this all in one big bracket with e to the x at the end. Because if I want to compare to the original, if I want to compare to what we've got written over here, the e to the x is at the end, so it's going to be much easier to compare if we put e to the x at the end. So what we're going to get, we've got x squared, we've got 2k, and we've got 2 x's. Then we've got k minus 1 plus 2k. Which means if I just put this in the nicer form, this is 2 lots of k plus 1x, like this. And what I can do is I can rearrange these brackets. This will be k squared minus k plus 2k. In other words, it will be k times by k plus 1, all times by e to the power of x. But this is exactly what we want. This means that the formula is actually true for k plus 1. This is because any time, if I go back to the original formula in terms of n, Anytime there was an n, we've now replaced it by k plus 1. So the n here, k plus 1. N minus 1 is now k. You can put that in full if you want. You can say k plus 1, k plus 1 minus 1 if you want. You don't have to spell that out fully. But essentially, that's the formula that we want for the k plus 1th derivative. So it's true for n is equal to k plus 1. Now the final step is the conclusion. And this is just the wordy part. It's nobody's favourite part really. We just need to write that up in words, probably repeating what I said earlier on. So the first point I'll make is that it's true for n is equal to 1. That's the base case. The second point I'll make is that if it's true for n is equal to k, then it's also true for 1 more than k. If it were true, that's what the inductive hypothesis said for k, then we also showed it was true for k plus 1, the next value along on the number line. That means if it's true for 1, it's true for 2. If it's true for 2, it's true for 3. If it's true for 3, it's true for 4. Therefore, final conclusion is that the formula is true for all n bigger than or equal to 1. You can say by mathematical induction if you want, but you don't actually have to. Well, there we have it, another question done. Try these extra 2 questions if you want more practice with induction derivatives.